This video will look at exam technique, and in particular we're interested in some topics within dynamics and control. What we will do is we'll give a walkthrough of how to tackle some exam style questions. And the key mechanism we're going to suggest to you is that you should begin by first summarising what you know about the particular topic. In this case, it's going to be systems and control. But always start by summarising, what do I already know? Often, the application of your core knowledge, what you already know, to the question will be obvious, especially when you think about it, and if you do this, it will make solving the rest of the problem far easier. So in summary, I'm repeating myself, what you need to do is practicing combining what you already know. So the key thing is identify what I already know, and then add that to the information that the question has provided. Once you've done this, you'll find it straightforward to get new information, and then you can repeat the procedure as you work through the problem. So let's just give a quick summary. What do I already know? And of course, these following slides are not intended to be comprehensive. They're illustrative, and it will depend on what topic you're doing. So this particular video is focused on first order responses and modelling. So we need to summarise, what do I know about first order systems? Well, the first thing is you're always advised, use a time constant form when you can. So you'll see that's what I've done here. I've said I can represent a first order model in a time constant form with time constant t and steady state gain c. If I need the response of that system for a constant u, I can write it down, and here you'll see I've given the standard solution, which I won't derive because you should have done that elsewhere. You'll remember the decay rate depends only on the time constant t. So you'll notice here I've marked some blue crosses to indicate clearly where the time constant, 2 time constants, 3 time constants, and so on appear. So this again is standard knowledge you should know about first order systems. You will also remember that you get 63% movement in one time constant. And finally, the steady state depends upon the term cu. So what I've done here in one slide is summarise the key information you should know about first order models and first order responses with constant inputs. Now, the other slides look at topics which are not covered in this particular video, and they're there for completeness because you will need these for other questions. Let's go straight to the question we're looking at today then. So, the concentration C of T of the product of a continuous chemical reaction is affected by some input f of t. Now, I'm not worried about what f of t is. It could be some dye or a chemical or something else. The concentration, you're told, can be modelled by a first order equation of this form: dc dt plus bc equals df, with two unknown constants b and d. Now, what I'm going to say to you is, as a general rule, don't worry yourself too much about the rest of the question at this point. First, start by saying, what do I know that I can add to just this preamble? Because if I add to this preamble, I may find that then when I start reading the bullet points, they're a lot easier to follow. Now, there is one other piece of information, however, which is key, that you're given a step response. That's just this top bit here, a figure, and that's this figure here. So now what I'm going to do is I'm going to go and I'm going to say, all right, what is it that I already know? So I'm beginning the question by saying, what do I know about mixing and reaction systems? Well, typically, these can be modelled by a first order model of this form: T dc dt plus C equals Kf. Now, what you will notice is I've deliberately ignored the equation I was given in the question. I've said, forget about that. What do I know? I know time constant form. So let's start with time constant form. So C, the concentration, T, the time constant, and K, the steady state gain. So what I'm going to do now is say, can I use time constant form because I understand that with the information provided and make some progress? So that's what we're going to do. So what information were you provided with? You were given that the flow rate goes from 0 to 0.005 and that you got this particular response. We've used our knowledge, this is what I already know, to say the time constant form is T dc dt plus C equals Kf. What next? Well, I happen to know that the change in Kf gives me the change in concentration here, which is 0.025. So I've got a very simple equation here. I already know that F is 0.005, and thus I can work out that K equals 5. So by putting the equation in time constant form, I can immediately work out the steady state gain K. What next? I also know for first order systems that I get a 63% movement in one time constant. So let's work out where 63% is. So here we go, 63% movement, so that's 0.63 times 0.025 gives me 0.16, and you'll see I've marked that with this line here, and therefore clearly that corresponds to one time constant, so one time constant must be 20, and therefore I can now write my model in time constant form as 20 dc dt plus C equals 5f. You'll see I've put in my value 20 for time constant, my value 5 for the steady state gain. Right, what I can do now is go back to the question. Well, the question said, I want you to use this model form, dc dt plus bc equals df, and I want to know what b and d are. And what we said is, right, we're going to ignore that and first start with time constant form. And so what we said is, well, I know the model is this. So all I need to do now is say, is there a relationship between these two models? Well, clearly there is. If I take the top model and multiply by 1 over b, then I get 1 over b dc dt plus C equals d over b times f. And clearly that tells you that 1 over b is the time constant, and d over b is the gain K. So what we get now is that 20 equals 1 over b and 5 equals d over b, which are easily solved to give b equals 0.05 and d equals 0.25. So you'll see by starting from time constant form, solving the question that was asked turns out to be quite straightforward. Next part of the question, sketch the expected behaviour if the flow is changed from a steady state 0.05 to 0.008. So again, this is a routine sketch question using standard data, and I just need to remind myself I'm going to use the time constant form because that's easier. So you see the time constant 20 and the steady state gain 5. So what have we got? At time 0, we were given the flow equals 0.05. I've written that again here. We know the gain's 5, so therefore C of 0 must be 0.025. So this is where I start. The flow changes to 0.08. I multiply that by 5, and I get that the steady state must be 0.04. The total movement is 0.015, so you can see that's 0.04 where you finish minus 0.025, which is where you start. So I've now got the total movement. Therefore I can work out the 63% movement, which corresponds to one time constant, so 0.63 times 0.015, that gives me this number here, and therefore I can work out the concentration after one time constant based upon where I start plus the movement. And there you have the value for C of t. I can also work out the value at 3 time constants using a 5% movement, so you're 5% away from steady state, and that's going to give you approximately 0.039. So I've now got all the data I need to do a simple sketch. So you'll see I've summarized the data up here. Okay, you see I've got start value, end value, value is at 1 time constant, value at 3 time constants, and what's the time constant. So the first thing to do now is create some graph paper. So we'll put some values in. You might get graph paper in an exam, but if you don't, a sketch like this can be done very quickly. So I've put in the basic values. We start at 0.25, we finish at 0.4. I'm now going to mark time constants because we know that the graph depends critically on those. So you'll see I've marked 1 time constant, 2 time constants, 3 time constants, which is 20, 40 and 60. I know that if the initial gradient will take me from the start point to the steady state in 1 time constant. So that helps me helps the sketch. So I draw the initial gradient. I know that after 1 time constant, I know what the value is, so I mark that on my graph. I know after 3 time constants what the value is, so I mark that on the graph. And then all I need to do is a smooth sketch taking the gradient information and those values. And there's the response that was requested. And obviously the examiner's looking for this point here, and this gradient. And obviously assuming that you've got the right values here on the left hand side and the right values here down at the bottom. What about the last bit, which is to test perhaps the students who want the very highest mark? So it's thinking, well, how do you think when something is a bit less straightforward? So it says, what happens if I increase the rate of production by 0.01 moles per meter cube per second? Okay, all you have to do here is plug the information provided into what you already know. So I'll show you that. Okay, what you already know is this equation here. dc dt plus bc equals df. And then what it tells you is that the rate of production, okay, so what's the rate of production? The rate of production is dc dt. So it tells you that dc dt is increased by 0.01. So that's all I've done, taking the equation that I've got for dc dt and added 0.01. And then over this side I've just rearranged it a bit by basically grouping some terms, you'll see, with these brackets. And why I've done that? Because again, it's now in a more conventional time constant form. The only difference is I can see that now df plus 0.01 are acting as a sort of combined input. So what can I see? There's no change in the time constant. Okay, I've got this equation in time constant form, and it's not affected by this 0.01 catalyst. So the time constant is not changed. However, the steady state has changed. The steady state increases by 0.01 divided by b. So hopefully what you can see is what might appear to be quite a difficult last part to the question, you can actually answer in very little space if you simply write down the information provided in a sensible manner. So that's the end.